Hello everybody, we are moving on to our next lesson in chapter 4, and today we are talking about one-to-one functions. So go ahead and take a moment to write down this definition and I will be explaining it. So a one-to-one function is when a function's inverse is also a function. We say a function is one-to-one if that original function passes the horizontal line test, and the domain of f is always the range of f inverse. This is our notation for f inverse. And the range of f is always the domain of f inverse. We can also write this as f inverse of x. Okay, but we'll still call that f inverse. All right, so let's determine if the following functions are one-to-one. Here's how this works. The vertical line test determines if we have a function. All right, we do have a function. However, the horizontal line test determines if the inverse is also a function. So because we do not pass the horizontal line test here, we hit our function twice. This means the inverse is not a function, which means we are not one-to-one. All right, whereas in this next problem, we pass the vertical line test, so this red curve is a function, and it also passes the horizontal line test. That means that this curve is a function and its inverse is also a function. And since we have a function either way, this is one-to-one. Now we can look at something instead of a curve. We're going to look at some ordered pairs. So we have x, y's. So first let's identify if this is a function. 2 goes to 6, negative 3 goes to 6, 4 goes to 9. Yeah, each input has only one output, so it is a function. But now let's look at the inverse. The inverse, if you remember, is when x's and y's are switched. So if we go ahead and write the inverse, which is just switching those x's and y's, now we'll see if this is a function, and we can see right here this is an issue because our 6 is going to two different outputs. So we're going to say no, the inverse is not a function, so this is not one-to-one. Okay, and again, being one-to-one means that a function or a function's inverse is also a function. Okay, so the original curve passes both the vertical and the horizontal line test. All right, so just to give you an idea of visually what inverses look like, the inverse of a function is always reflected over the line y equals x. And again, that's because the x's and y's just switch places in the inverse. So if we graph this, here is the line y equals x right here. It's going to essentially be a mirror image on either side. So here's how you would do this. This point right here is negative 4, negative 4. Well, when you switch places, those flip-flop, you're still at negative 4, negative 4. Here we're at negative 3, 0. So the inverse will be at 0, negative 3. Here I'm at 0, 2. So the inverse will be at 2, 0. Again, x's and y's are just switching. And finally I'm at 1, 5. So 5, 1. And what happens is when you connect your dots, you see you do get a mirror image there. Pretty cool, right? All right, so next we have this notation here. This is f inverse. We're going to identify the range of f of x. An important thing to remember is that when you're dealing with the original function and the inverse, the domain and the range switch places. So if I'm asking for the range of f of x, this is really asking for the domain of f inverse. All right, so be careful with that. So I'm looking at f inverse, this guy right here, and I'm finding the domain of that, meaning what can x be? Well, this guy right here cannot be a negative because it's under a square root, but it also is in the denominator, so it also can't be 0. So I'm going to say greater than 0. and solve it. And I know x has to be greater than 5/2. Now here's where you need to be careful, because this is an x. It's talking about a domain. You're really being asked for the range. So now instead of dealing with an x, you are dealing with a y. Y such that y is greater than 5/2, because they're asking for the range. Or what I prefer to do is just use interval notation, because that doesn't have an x or a y and I can't mess it up. So greater than 5/2 is just 5/2 to infinity, done. Okay, whereas I feel like if you use set notation, you may accidentally put an x, because that's what we had over here. Just something to think about. All right, so in our last lesson, we found f of g of x and g of f of x. And what I mentioned was that this has to do with inverses. So it turns out that if you do both of these composite functions and you get x for both, it turns out that those functions are inverses. So we are just going to do f of g of x and g of f of x for both functions and show that we get x for both and that we, yay, have inverses. All right, so this is not going to be terribly fun, but we're going to do it anyways. Where am I? Here we go. All right, so I'm going to start with f of g of x, which means I'm taking this and it's going there and it's going there. Yes, I know. All right, so let's just take a minute and plug it all in. All right, now one strategy you can use here is we can try to cancel the 1 minus 2x's, because notice that both your numerator and denominator have that 1 minus 2x. So essentially what we're going to do, or what I would suggest you do, instead of trying to get a common denominator on top and bottom, I would just try to get rid of the 1 minus 2x right now. So I'm going to multiply the top and bottom by 1 minus 2x. And essentially you're distributing this, but what's going to happen is it's going to cancel these guys. Just make sure, and I've written this way too big, that when you do that, it's still distributing to this 3. All right, so it's like you're distributing the 1 minus 2x to each part. 1 minus 2x to the first part, the 1 minus 2x's cancel, you're just left with the 3x plus 5. 1 minus 2x distributes to the negative 5, that's going to be a negative 5 plus 10x. Over 1 minus 2x distributes to this first part, they're going to cancel, but you still have this 2 out front that's going to distribute, so that's a 6x plus 10. And then 1 minus 2x multiplied by that 3 is a 3 minus 6x. And then we can go ahead and combine. I'm going to get a 13x on top because my 5's cancel, and I'm going to get a 13 on the bottom because my 6x's cancel, and lo and behold, 13x divided by 13 is x. All right, so now let's try it the other way, because we get to do this a second time. G of f of x, and we are just going to use the same strategy. This guy is going there and there. So I have 3 x minus 5 over 2x plus 3 plus 5 over 1 minus 2 x minus 5 over 2x plus 3. And this time, again, instead of distributing or trying to find a common denominator, I just want to get rid of the 2x plus 3's. So I'm going to multiply by 2x plus 3 on top and bottom. And again, it's like you're distributing, but your 2x plus 3's will cancel. So on top, I'll get a 3x minus 15. And I'm distributing my 5, a 10x plus 15. And then down here, 1 times 2x plus 3 is just 2x plus 3. And when I distribute here, 2x plus 3's will cancel. You still have this negative 2 multiplying though, so that's a negative 2x plus 10. And actually, the same sort of thing happens. We have a 3x plus 10x because the 15s are canceling. And on the bottom, we have a 3 plus 10 because the 2x's are canceling. And we have a 13x over 13, which is just x. And a reminder from when we talked about property of functions, even and odd functions, you do need to provide some sort of summary statement here. So this doesn't need to be like, you know, a huge long statement, but I would say something like, since f of g of x is equal to g of f of x is equal to x, f and g are inverses. Okay, so that's just summarizing what we just discovered. Last two. The given function is one-to-one. Find its inverse and check your answer. State the domain of f using f inverse. Okay, so one way that people like to do this is make a table. So this is f of x, f inverse, ooh, that was very large, domain, range. This is helpful to people sometimes. So if we look, we have f of x right here, and we have the domain. Okay, we've been given the domain of f of x. So this is just x such that x is greater than or equal to 0. What's nice about that is that you've also now found the range of f inverse, y such that y is greater than or equal to 0. Because remember, these two match. You just have to change your numbers. Or we could write this as 0 to infinity. I just used the same notation that was here. 0 to infinity. So now we are trying to find the domain and range of f using f inverse. Let's go ahead and find the inverse first. In order to find the inverse, what we are doing is switching x and y. So what that means is instead of y equals x squared plus 4, I'm going to have x equals y squared plus 4. And now I'm just going to go ahead and solve for y. So I'll subtract my 4 over, and then I'll square root both sides. Now, ordinarily, we would say plus or minus x minus, or square root of x minus 4, right? Because when you square root both sides, you get a plus or minus. However, let's look back at our domain here. We were told that the domain of our original function was greater than or equal to 0, which meant that our range for the inverse is greater than or equal to 0. See, we wrote it right here. Y has to be greater than or equal to 0. So that means that we do not need the plus or minus. This has to be positive. Change this back to an f inverse. Okay, so now this is our inverse. Now what we're going to do is we're going to find the domain of this guy. And by finding the domain of f inverse, that will give us the range of f. Okay, and if you notice, it said find the range of f using f inverse. Okay, that's the easiest thing to do. So now this guy, we know x minus 4 has to be greater than or equal to 0, right? Because we can't have a negative underneath the square root. So x has to be greater than or equal to 4. So over here, that's the domain of f inverse, which means our range is the same thing. You just need to make sure that you switch this to y's, or you can go ahead and you can use interval notation, so you don't have to worry about that. Oop, that's a bracket. All right. So there you go. The things that we're actually being asked to find are just domain and range of f. So this guy right here. But if the table helps you, then go for it. All right, last one. This is a good one. I'm going to go ahead and I'm going to write my table. And I have domain range f inverse. Okay, this guy right here is a y, so we're going to find the inverse first. I guess technically we could find the domain of f of x first if you want. So here's f of x. You should be able to look at this and say, oh, x can't be -2. So it's the domain of f of x. So that means that the range of f inverse is y such that y can't be -2. Okay, because again, the domain of the one is the range of the other. So now, usually what I do is I just find the domain of both f and f inverse and then use that to find the range of the other two. Because domain is easier to find without an actual graph, essentially. All right, so this is a y, and now they're going to switch places. X equals 3y minus 4 over y plus 2. And when in doubt, cross multiply or multiply both sides by y plus 2. And we're going to get this. And then basically what you're going to do is distribute, and we can get all of our y's on one side and then just factor a y out, because remember the goal is to actually solve for y. All right, so I'm just going to move some things around. I'm going to bring my 3y over, make sure you subtract it. I'm going to subtract my 2x. And now we can see, since our y's are together, we can factor a y out. And then final step is go ahead and divide by that x minus 3. All right, and then don't forget to rewrite this as f inverse. That's something people forget a lot. Okay, so here is my inverse. And now we're going to look at this and we're going to determine the domain of this guy. Well, x can't be 3, right? So that's the domain of f inverse, x such that x can't be 3. So that means that's the range of f of x, y such that y can't be 3. Now, last thing, I just want to bring this back to our rational functions from last chapter, and just looking at why these domain and ranges are what they are. So if you look at our original function, you should know that you have a vertical asymptote at x equals -2. That's why our domain is what it is. But you should also see that you have a horizontal asymptote at y equals 3. Okay, because we have the same degree, and the horizontal asymptote is the ratio of the lead coefficients in this situation. So that is why your range is y such that y can't be equal to 3, because you have a horizontal asymptote there. And we can also see that happens in f inverse. Here you have x can't be equal to 3, so that's the domain of x inverse, because the inverse has a a vertical asymptote at x equals 3. But then look at what its horizontal asymptote is. It's a -2. That's why for the inverse, the range is y such that y can't be -2. So essentially our domain and range, when they flip, that flips your vertical and your horizontal asymptotes for these two functions, which I think is pretty cool. Have a great day. Bye.